Welcome back. This is the second part of Lecture 5 on discrete probability distributions. And in the first part, we looked at what a probability distribution was, and then we looked at binomial probability distribution. And now what we're going to do is we're going to start to look at hypergeometric probability distribution. And we're going to finish up the chapter by looking at the Poisson distribution. So, first we'll start off with the hypergeometric probability distribution. And for the hypergeometric probability distribution, one key thing is in the real world, most sampling is done without replacement. Thus, if the population is small, the probability for each observation will change. So, what we mean by that is if we're selecting a sample from our population, we normally don't select one item or person and then put them back into the population and then select our next choice. We normally select a choice and then select another choice without putting the first choice back. So that's what we mean when we say without replacement. If we think about this with a deck of cards, if we're drawing two cards without replacement, that means that we draw the first card and then we draw the second card, but now there's only 51 cards left in the deck instead of 52. So, if the population is small, the probability for each observation will change. And this is very similar to the blue umbrella question that we did in lecture 4, where we had 12 umbrellas in total, and 3 of them were blue. Well, once we sold the first umbrella, and we assumed it was blue, we only had 2 blue umbrellas left out of 11 umbrellas. So the probability changes from selection to selection. And if you recall, one of the criteria for the binomial distribution is that the probability of success remains the same from trial to trial. Well, in small populations without replacement, that doesn't occur. Since the probability of success does not remain the same from trial to trial when sampling is from a relatively small population without replacement, the binomial distribution should not be used. Instead, the hypogeometric distribution should be applied. So, if a sample is selected from a finite population without replacement, and if the size of the sample, little n, is more than 5% of the population, which is denoted capital N, then the hypergeometric distribution is used to determine the probability of a specified number of successes or failures. It is especially appropriate when the size of the population is small. So if you come across a question and in the question it mentions the size of the population and the size of the population is small, that should be an indicator that we need to double check to see if we have to use hypergeometric probability distribution. So we'll go through the formula and then I'll show you how to do this in Excel. And the formula for hypergeometric distribution is as follows. The probability of x successes is equal to, and we have 3 combination questions. S choose x, where S is the number of successes in the population, and x is the number of successes in the sample, times capital N minus S, choose small n minus x. And capital N minus S is the size of the population minus the successes in the population. And we're going to choose n minus x, which is the sample size minus the number of successes in our sample. And then that's going to be divided by the size of our population, choose the size of our sample. So 3 separate combination questions here. Now, I'll show you how to do this in Excel, but I'll show you how to use the formula first. So, marbles in an urn. Assume, for example, that there are 5 green and 45 black marbles in an urn. Standing next to the urn, you close your eyes and draw 10 marbles without replacement. What is the probability that exactly 4 of the 10 marbles are green? So, we've got all the information we need here. We've got a small population. Our population is 50. Our sample size is 10. So that's well over 5% of the size of our population. It's actually 20% of our population size. So we definitely need to use hypergeometric distribution in this. So first off, we need to identify some items here. The size of our population, capital N, is 50. The number of successes in our population is 5. And the size of our sample, little n, is 10. We're looking for the probability that we draw exactly 4 green marbles. So, probability that x equals 4 is equal to number of successes in the population, choose number of successes in the sample, so 5 choose 4, times the remaining number of marbles in the population, choose the remaining marbles in the sample that are not green. So here we've got 45, choose 6. And we're going to divide that by our size of our population, choose the size of our sample. So 50, choose 10. And we can do this in our calculators. We can use Excel and use equal combin if we want. But either way, when we solve these out, we'll get 5 times 8,145,060. And that's going to be divided by 10,272,278,170. And when we do that, we're going to get a very small probability. Our probability is equal to 0.003965. So, therefore, there's a 0.0040 or 0.4% chance that if 10 marbles are selected without replacement at random, exactly 4 of them will be green. It's really easy to get confused with this formula or make little errors with it. So, the good news is we can do this in Excel. And when we do this in Excel, it does all the work for us in the background. Excel will just need to know the size of our population, number of successes in our population, and the size of our sample. Excuse me. All right. So, when the binomial requirement of a constant probability of success cannot be met, the hypergeometric distribution should be used. Rule of thumb, if the selected items are not returned to the population or selected without replacement, and the sample size is less than 5% of the population, we can still use binomial distribution. If the sample size is greater than 5% of our population, we need to use hypergeometric. So, in Excel, our command for hypergeometric distribution is equal hypgeom.dist. So, going back to our marbles in an urn question, I'll walk you through how to do this. So, the first step is we're going to create the probability distribution. We're interested in the number of green marbles. Well, when we select 10 marbles at random out of the urn without replacement, we can get 0 green marbles, 1, 2, 3, 4, or 5 green marbles. There's only 5 in the entire population, so that's why we only go up to 5. So we created our probability distribution in Excel. Next, we have to define what's the sample size. And in this case, we're drawing 10 marbles without replacement, so little n is 10. Next, we have to denote the number of successes in the population, S. And there are 5 green marbles in the entire population, so S is 5. Finally, we have to define the size of the population, which is denoted as capital N. And here, capital N is 50. We have 45 black marbles, 5 green marbles, so total of 50 marbles. And Excel, when we go to use hypergeometric distribution, is going to ask us for X, which is from our probability distribution. We'll put a comma, then it's going to ask for a sample size, or little n. Then we'll put a comma, it's going to ask us for number of successes in the population, or S. And then we'll put a comma, it's going to ask us for the size of the population, which is capital N, in this case 50. Finally, we'll put a comma, it's going to ask us, hey, true or false? True for a cumulative hypergeometric probability distribution, false for a regular hypergeometric probability distribution. And so that true and false is the exact same as we saw with binomial distribution. So to create a hypergeometric probability distribution in Excel, step 5, we use the command equal hypgeom.dist to complete the hypergeometric probability distribution. Excel will first want to know the value of x, then the value of little n, then the value of s, then the value of capital N. And finally, it'll ask you if you want a cumulative probability or not. True is a cumulative probability, false, regular probability. Now, just like with the binomial distribution, for little n, s, and capital N, we can use the actual values, so we can put the actual values in, or we can choose the cell where we've put that information. If we choose the cell, really important again to use absolute references, because we're going to be dragging this formula, and we do not want Excel to be looking at any other cells for little n, s, and capital N. So we have to lock them in place with absolute references. You'll also notice that in Excel, I've set it up so that the order that Excel asks you for information is the same order that I've got my variables in. It's first going to ask for X, which we get from our probability distribution, then little n, then S, then big N. I recommend doing it that way, setting it up that way. It just makes it nice and easy so you don't really have to think about, oh, what am I going to select? So our formula for this is equal hypgeom.dist. And then we're going to start off, it's going to ask for X. We're just going to select A8. Don't absolute reference that. We want that to change with the formula. We're going to put a comma. It's going to ask for little n. We can either put 10, or if we're referencing the cell, make sure to do an absolute reference. So that is in cell B3. So we'd have to do $B, $3, then comma. It's going to ask for S, same thing, $B, $4. And then finally it's going to ask for capital N, so comma, $B, $5. And then finally, after we put a comma, it's going to ask us for true or false. We're going to say false. We want a regular probability distribution, and that's because we're looking for the exact probability that 4 of the 10 marbles are green. So we do that, and we look down here. For x equals 4, our probability is 0.003964583. That should look pretty familiar because that's what we did with the formula. So, probability of drawing 10 marbles without replacement and drawing exactly 4 green marbles is 0.0040, or 0.40% chance. All right, so let's take a look at another example. A team is being assembled to conduct a research study on a new type of diabetic medication. The research team will consist of 8 members. 12 women and 10 men apply for the team, and the members will be selected by a lottery system, so just randomly selected. What is the probability that exactly 6 of the 8 members will be women? So, if we're going through here, we're selecting a research team of 8 members, so that's our sample size. Little n is going to be 8. How many successes do we have in the population? Well, we're interested in knowing the number of women on the committee. There are 12 women in the population, so S is 12. We have 12 successes in the population. Finally, what's the size of our population? Well, our population is 12 women and 10 men. So our population size is 22. Now we're ready to go and use hypergeometric distribution to find out the probability that exactly 6 of the 8 committee or research team members will be women. So, in Excel, we've got sample size of 8, number of successes in the population is 12, size of the population is 22. Now we can just go and do our hypergeometric distribution. So equal hypgeom.dist, and then we're going to select x followed by little n followed by s followed by capital N, and then we're going to say false because we want a regular probability distribution. And we know that because we want to know the probability that exactly 6 of the 8 members will be women. So if we look here, well, the probability that exactly 6 of the 8 members will be women is 0.1300, or 13% chance that our 8 member research team will consist of exactly 6 women. All right, so let's look at another example here. And we're going to use the same research team example here. A team is being assembled to conduct a research study on a new type of diabetic medication. The research team will consist of 8 members, 12 women and 10 men apply for the team, and the members will be selected by a lottery system or just randomly selected. What is the probability that at least 3 members will be women? So, at least 3. This tells us, oh, okay, we're not looking for an exact probability. So we'll probably end up using a cumulative probability distribution. So just putting in true at the end of our Excel formula. Now, what does this actually mean? Well, we want to find out what's the probability that on our committee we have either 3 women on the committee, 4, 5, 6, 7, or 8 women on the committee. So the way we're going to do this, we're going to use hypergeometric distribution. We're going to do a cumulative probability, and we're going to use our complement rule. So remember, our cumulative probability does that number and fewer. What's the probability of that number and fewer? So since we want to know the probability of 3 or more, what we'll have to do is find the probability for 2 or fewer women on the committee. And then we'll use our complement rule to find out the probability that at least 3 members will be women. Let's take a look here. So, as I said, we have 2 ways of figuring this question out. We can use the false statement in the hypergeometric distribution formula and simply add the probability for 3 women all the way up to the probability for 8 women. So 3 plus 4 plus 5 plus 6 plus 7 plus 8. Or we can use the true statement and use the complement rule. So the probability that x will be greater than or equal to 3 is equal to the 1 minus the probability that x is less than 3. So I'm going to use option 2 here. And we can see I've done my regular probability distribution here. Over here, I've done my cumulative one. So once again, put it in the exact same way I would do for my regular hypergeometric distribution. But at the end, when I put my comma, instead of putting false, I'm going to put true for a cumulative total. And this is what we'll get. Now, what do I want to do? Well, I want to do 1 minus the probability of 2 or fewer women on the committee. So that's going to be 1 minus cell C10 here, or 1 minus 0.047987. And when we do that, we'll find out that the probability that at least 3 members of the research team are women is 0.9520, or there's a 95.2% chance that at least 3 members will be women on the research team. And that's hypergeometric distribution. So, once again, hypergeometric distribution, we use that when we have a small population and we're making selections without replacement. If we want to make sure that hypergeometric distribution is the way to go, we'll take our sample size, divide it by our population size, and if our sample size is greater than 5% of our population size, we'll use hypergeometric distribution. So now we're going to move on to our final discrete probability distribution, and that's explain the assumptions and compute probabilities for a Poisson distribution. The Poisson distribution is named after the French mathematician Simeon Denis Poisson. And the Poisson distribution is useful when there are a large number of independent trials with a small probability of success on a single trial, and the variable occurs over a period of time. So the Poisson random variable x is often a model for data that represent the number of occurrences of a specified event in a given unit of time or space. So some examples of where we could use the Poisson distribution is the number of calls received by a receptionist during a given period of time, the number of medical instrument breakdowns in a day, or the number of traffic accidents at a given intersection during a given time period. So, once again, we're looking at the occurrences of specific events over a given period of time or space. So, the Poisson distribution is based on the Poisson process. And the following statements describe what is known as the Poisson process. Number one, the occurrences of the events are independent in an interval. Number two, an infinite number of occurrences of the event are possible in the interval. Number three, the probability of a single event in the interval is proportional to the length of the interval. And number four, in an infinitely small portion of the interval, the probability of more than one occurrence of the event is negligible. So, what we're really looking at here is number one, if an event occurs, it doesn't have an impact on whether or not another event will occur. For number two here, it is possible to have an infinite number of occurrences of the event in a time interval. It's just the more occurrences we're looking at in a certain time period, the less likely it is to happen. Number three, when we look at the probability of a single event in the interval is proportional to the length of the interval. That should make some sense. The longer the time interval, the more likely that an event is going to occur within that interval. If it's a really, really small interval, the less likely it is for that event to occur in that interval. And that kind of ties in with number four, where if we get into really, really, really small section of the interval, the probability of more than one occurrence of the event is probably not going to happen. So it's negligible. So how do we calculate the Poisson process or the Poisson distribution? Well, there's two ways. We can use the formula, and here is the formula. The Poisson distribution can be described mathematically by the formula. The probability of x occurrences is equal to the mean number of occurrences over that time period raised to the exponent x, or the number of occurrences we're looking for, times e, which is a constant 2.71828, to the negative mean divided by x factorial, where once again x is the number of occurrences or successes. So all we really need to know is the mean per time period, the mean number of occurrences per time period, and we can do this question using the formula. Or we can use Excel to do it, and once again, we'll just need to know the mean over that certain time period. So the Poisson distribution depends on a single parameter, mu, which is the mean. And here, the parameter mu represents the expected number of events over time period t. So what we're really looking at is, hey, on average, how many of these events can we expect over a certain time period? One important difference between the Poisson and binomial distributions concerns the number of trials and events. As we know, for binomial distribution, there are a finite number of trials, n, and the number of events can be no larger than n. For a Poisson distribution, the number of trials is essentially infinite, and the number of events, or number of deaths, if that's what we're looking at, can be indefinitely large. Although the probability of x events becomes very small as x increases. And we'll see examples of this as we go through. So let's take a look at a question. If there are 500 customers per 8-hour day in a checkout lane, what is the probability that there will be exactly 3 in line during any 5-minute period? All right, so there's a couple things. For the Poisson distribution, we need to know the expected number of occurrences, or the average number of occurrences over a time period. And here they give us 500 customers per 8-hour day. That's an average, but that's 500 customers over an 8-hour day. We're interested in how many, or what's the average or expected number of customers in any 5-minute period. We need to know that average so then we can do this question and find out the probability that there will be exactly 3 customers in line during any 5-minute period. So we have to convert the average we have into the time period we're looking at. So there are 60 minutes, and we want to divide those by 5 minutes in each hour. So 60 minutes in an hour. We want to divide that by 5 minutes because we want to find out 5-minute increments. So we'll do 60 divided by 5 minutes. Basically, there's 12 5-minute periods in an hour. We then need to multiply that by the 8 hours, and we'll find out, well, our 8-hour day really consists of 96 5-minute periods. So, if we want to find the number of the expected number of customers in a 5-minute period, We have to take the 500 customers in an 8-hour day and divide it by the 96 5-minute time periods in an 8-hour day. So the expected value during any one 5-minute period would be mu equals 500 divided by 96, or 5.2083. Once we've got that, we're just going to use our Poisson distribution formula. So probability of X occurrences is equal to the expected number of occurrences raised to the number of successes times E to the negative, raised to the negative expected number of occurrences divided by X factorial. All right, so in this case, X is 3 because we want to know the probability that there will be exactly 3 customers in line during any 5-minute period. So P of 3 equals our average or expected number of customers in a 5-minute period, 5.2083, raised to the exponent 3, times E raised to the negative mean, or negative 5.2083. And all that's going to be divided by 3 factorial. And we can do that in our calculators, and we'll find the probability that there'll be exactly 3 customers in line during any 5-minute period is 0.1288, or there's a 12.88% chance that we'll have exactly 3 customers in line at any during any 5-minute period. So a lot going on there. The biggest takeaway here is if the question gives us an average but it's not in the right time period, we have to convert it to the proper time period before we can attempt the question. Let's look at another example. We're going to look at the exact same example, but I'm going to show you how to do this in Excel. So in Excel, what we need to know is we need to know the mean, or expected number of occurrences in the time period. In this case, we need to know the expected number of customers in a checkout lane during any 5-minute period. But we already solved that in the previous question. Our expected number of customers in any 5-minute period is 5.2083. And that's all the information we need for Excel to calculate out the Poisson distribution. In Excel, we're going to use the formula equal Poisson.dist. Excel will first want to know the value of X, so we get that from our probability distribution. Then when we put our comma, it's going to ask for the value of the mean, or the expected number of occurrences in that time period. We'll put that in, we'll hit comma, and then just like with binomial distribution and hypergeometric distribution, it's going to say, do you want a cumulative total? If so, true. Or do you want a regular distribution, in which case, false. So, true equals cumulative probability, false, regular probability. And once again, use absolute references in Excel for our expected number of occurrences per whatever the time interval is, um, or put in the actual value for mu. So let's see this in Excel. If we know our average or expected number of occurrences in a given time frame, and we do in this case 5.2083, then we just set up our probability distribution. And now we can do equal Poisson.dist. In brackets, we're going to select X, put a comma. We're going to absolute reference our mean or average. And then we're going to put a comma. In this case, we're going to say false. We want a regular probability distribution. Now we're just going to grab that formula, drag it down over all our outcomes for X, and we could have extended X, by the way, indefinitely. You know, if they're having a super blowout sale, we might have 150 people in a checkout lane at one during one 5 minute period. Um, so it could get infinitely large, but our probability of that happening will get smaller and smaller and smaller the larger X gets. In this case, we're just curious about the probability of exactly three customers being in line during any 5 minute period, and that's going to be 0.1288, or there's a 12.88% chance. All right, try this one here. So, in a study of drug induced anaphylaxis among patients taking rocuronium bromide as part of their anesthesia, Lake and Rottingen found that the occurrence of anaphylaxis followed a Poisson model with an average of 12 incidents per year in Norway. Find the probability that in the next year among patients receiving rocuronium, exactly 4 will experience anaphylaxis. So the good news here is we're dealing in the same time frame as the time frame given to us for our average here. So we don't have to convert our expected number of occurrences. So we can just use Excel, give it a shot when you're ready, uh, or pause the video, give it a shot, and then when you're ready, press play and resume the video and see if you got it. All right, so since we want to know the probability of exactly 4 occurrences in the next year, we're going to do just a regular probability distribution. So we set up our probability distribution, and we could have gone on and on and on forever here, but I just did the first 5. We're interested in exactly 4 will experience anaphylaxis. So we're going to put into our probability distribution the Poisson formula, equal Poisson.dist, in brackets, select X, comma, select the expected number of occurrences during that time period, comma, false. And what we'll find out is the probability that in the next year among the patients receiving rocuronium, exactly 4 will experience anaphylaxis is relatively low. It's 0.0053 or 0.53%. Last question here. I want you to try this one. Once again, same question we just looked at, except now that we want to find the probability that in the next year among patients receiving rocuronium, no more than 5 will experience anaphylaxis. So 0, 1, 2, 3, 4, or 5, but no more than 5. So here's your little hint. You're probably going to want to use the true statement when you do this in Excel. So I recommend pausing the video, trying this question, then resuming the video to see if you got it right. Excuse me. All right, let's take a look here. So, our average or expected number of occurrences of anaphylaxis in a year is 12 incidents per year in Norway. And that's what we're going to use as our fundamental base for this. Our formula is going to be equal Poisson.dist in brackets, select X, comma, select our expected number of occurrences over the next year. In this case, that's 12. Or we can absolute reference the cell, $B, $3, Then we'll put a comma, and this time we want the cumulative probability, so it's true. And then all we have to do is look at x equals 5 here. And this is the probability, because this is a cumulative total. This is the probability of 0, 1, 2, 3, 4, or 5 occurrences in the next year. So, the probability that in the next year, among the patients receiving rocuronium, no more than 5 will experience anaphylaxis is 0.0203, or there's a 2.03% chance that no more than 5 will experience anaphylaxis. And that is it for lecture 5, part 2. I hope you enjoyed that. If you have any questions, as always, feel free to email me and I'll help you out. Or if you need a little bit more guidance, email me and I'll do what I can. Hopefully, you enjoyed that and learned something in there. And thank you very much for listening. We'll talk to you again in the near future. Take care.